Okay, so hello everybody. So our wonderful workshop is slowly approaching the end, or maybe taking into account the research interest of our speaker, I should say dynamically approaching the end, but still we have two talks. Okay, and the first of the two remaining talk would be by Professor Yonatan Gutman. So before he starts his talk, let me say a few words about him. So he's from the Institute of Mathematics of Polish Academy of Science, and Yonatan studies topological dynamics and ergodic theory. He obtained his PhD in 2009 from the Hebrew University of Jerusalem, and 8 years later, he obtained his habilitation at the Institute of Mathematics of Polish Academy of Science. He is an author of more than 30 publications published in prestigious journals. And also he was awarded with many grants, for example, Opus Grant, Sonata, Maestro, also Marie Curie Career Integration Grant. He is also the winner of National Science Center Prize in Exact Sciences and the prize of the Minister of Education and Science for significant achievements in scientific activities. Both those prizes were in 2021. So after this quick introduction, I think that we are all ready and eager to listen to his talk. So Yonatan, please, the Zoom is yours.
Thank you very much for the invitation and for the introduction. One correction, I did not receive a Maestro grant. I was a member in the Maestro grant of Professor Tomasz Dovnarowicz.
Okay, so sorry for that.
Okay, so is my slides visible now? Are my slides visible, excuse me?
Yes, the first page of your slides is visible.
I'm trying to... Second.
We can see the cursor of your mouse, but still we are seeing the front page of your presentation.
Oh, okay. So now do you see it when I move it?
Yes.
All right. Okay. So the title of my talk is Nilspaces and their applications. And of course, I will explain what are Nilspaces. This subject originates in the work of Balázs Szegedy about around 2010. And he based this, so Nilspaces is a category of mathematical objects, and he based this category on a previous category called the parallelepiped structures by Host and Kra, which is from about, I think, 2005. And so we are talking here about around a decade of research. I must say that recently it seems that this subject has achieved a certain maturity. I was one of the organizers together with Szegedy, Candela, and Franzikinakis of a workshop in June in Bendlevo, which was about Nilspaces, and we had about 50 participants from many fields from all around the world. So I think this subject is really ready for the next step. Okay, so because Nilspaces is quite an abstract concept, I chose to start with one application, and then from this application understand how this subject arose, and then after that I will give the exact definition, so we will see. So Nil spaces are related to another concept which is called the Nil sequences. I will give the exact definition later, but Nil sequences are sequences that come from Nil systems, which are dynamical systems on Nil manifolds. And they appear in many guises in several areas of mathematics, so in topological dynamics, in ergodic theory, in additive number theory, and in additive combinatorics. So let's start with this third subject. So we will start with a very famous result under the title of linear equations in primes. So in order to introduce this, let P be the primes. And consider the following system. X is in P and X plus 2 is in P. And we want this to hold infinitely many times. So this is, of course, the famous twin prime conjecture. Are there infinitely many twin primes? This is open question, and it's quite an old question. Now let us consider the system 4x plus 3y is a prime, x is an integer, and y is an integer infinitely many times. This system we can solve because by Dirichlet's theorem, ax plus b contains infinitely many primes if a and b are co-prime. So we can just set y equals 1, for example, and we get infinitely many solutions. Now, what about the following system? 4x plus 3y is a prime, x is a prime, and y is a prime. So this is, of course, seems much harder than the first system. And actually, you can solve this infinitely many times. And this follows from the paper by Green and Tau, Linear Equations in Primes from 2010. Now, one could rewrite this problem, as just that the following sum, 1px, 1py, 1p4x plus 3y diverges. Right? Then we will have infinitely many solutions. Now, let us take the approach that we want to finitize the problem. So let us try to establish instead that when we take this normalized average, 1px, 1py, 1p4x plus 3y, now x and y goes from 1 to n, then let's say the lim sup is positive or lim inf. Now, this approach will not work. And the problem is that the primes are not dense. They constitute 0% of the natural numbers. Now, the way Green and Tau approached this problem was that they used something called transference principle. And this transference principle, which I will not discuss, allowed us to transfer the problem into the realm of random dense set of the integer, so to sets which have positive density. This principle was first used in their famous theorem from 2004, which states that the sequence of prime number contains arbitrarily long arithmetic progressions. So this is a particular case of solving linear equations in primes. And so we will now, without discussing the details, and the details are complicated, we will just replace P by a set B with positive upper density. So this is this assumption. And we will try to, we will discuss the following system. X is in B, X plus Y is in B, X plus 2Y is in B, and X and Y are integers infinitely many times. So we are actually looking for infinitely many non-trivial three-term arithmetic progressions in a set of positive upper density. And so we are actually in the framework of Semeredi's theorem. So Semeredi showed that this is also a very famous theorem, that any set of positive upper density contains k-term arithmetic progression for k as big as you wish. And actually, as you can see, we can of course find for a fixed k, we can find infinitely many. And so we will now use the strategy which we tried before, which was finitizing the problem and establishing the following limb soup is positive. Now it's common in this area to embed the first n integers in a cyclic group where P is some multiple of n. This is useful because then we have a field, so we can divide. So we just consider the following problem. So you see, instead of x and y between 1 and n, we take now x and y in ZP, and we looked at 1ax, 1ax plus y, 1ax plus 2y. Obviously, this the addition here is modulo P. So obviously, this adds some non-legal, let's say, arithmetic progression, but this is really negligible. And now comes the first non-trivial observation. So when you look at this expression, you see it's not symmetric in x and y. And usually in mathematics, symmetry is good. So we want to try to symmetrize it. So if you use the Cauchy-Schwarz inequality several times, you can show that this expression that we saw, its force power is actually bounded by the expression which I wrote here, which is symmetric. So here we have, okay, I should have said that when I use the notation E, so expectation, and everything is in a finite cyclic group, I just mean that I take counting normalized. So in this case, for example, I have 4 variables. So I will normalize with 1 over p to the 4th, and then I will just take the sum. In any case, you can show by using Cauchy-Schwarz that this expression is bounded by the expression here. And as you can see, this expression 1a, a plus d prime, a prime plus d, a prime plus d prime, this looks symmetric, right? No letter here has a special role. And actually, this is a particular example of the so-called Gauss norms. So Gauss introduced something which he called uniformity norms of order d for d integer. Today we call it Gauss norms. And this is for a finite abelian group. You take the average, the normalized average over certain products. And what you can see in this product appears something which is called the d-dimensional parallelepiped. Because, of course, this is a discrete parallelepiped. You take here x plus h1 omega 1 up to hd omega d, and the omegas are 0s or 1. So this looks like a parallelepiped rooted at x. Notice that it's, of course, it's non-trivial. This is a norm. It's even non-trivial. This is non-negative, this expression, but it is. And so the above inequality is a particular case of the so-called generalized von Neumann theorem, which states that this expression, which you can think about as a generalized arithmetic progression, because we have here f1 a plus d until fk minus 1 a plus k minus 1 d. This is controlled by the suitable Gauss norms. This is very useful. So the symmetry here really helps. In some sense, it allows us to go from an expression counting arithmetic progression to studying the Gauss norm, which is a more symmetrized object. So there is some chance that we will be able to say more things about it. This was the approach of Gowers that was, of course, successful. Let us then pursue this. So assume A has density alpha in the set of integers from 1 to n, and then we define the balance function fa, which is alpha 1n minus 1a. So we balance our original indicator function on the set A such that the expectation is 0. And then we define a multilinear functional. Tf0, Tf1, Tf2 is just the unnormalized sum over the three-term arithmetic progression. And now we notice that this multilinear functional gives us the number of three-term progression in A when we, of course, take T1A, 1A, 1A. Notice that this also includes trivial three-term progression. So we should remember that, because we are, of course, not interested in arithmetic progressions where the difference is 0. That's trivial. In any case, we can use multilinearity in order to write this expression as a sum of 8 expressions. In particular, 7 of these terms. So here actually I developed, or I wrote 1a as alpha 1n minus fa, used multilinearity, wrote the 8 expression, and notice that 7 of them include f of a. And this is useful because then we can apply the generalized von Neumann theorem and bound each one of these 7 terms by the 2 Gowers norm of fa. Of course, we need because everything here is non-normalized, and the generalized von Neumann theorem was with normalization, we have here some constants appearing. Also, I remind you that we work in ZP, where P is Cn for some C. But the gist of this is that the number of APs in A minus this expression, which is actually counting the number of three-term progression in N times alpha to the third, which you can also show is the number of three-term progression in a random set of density alpha. And this is of the order alpha to the 3n squared. So in any case, we get that the number that we are interested, the number of 3 APs in A, minus the number which is easy to calculate for a random set of density alpha, is controlled by the Gowers norm. And then we have a dichotomy. Either this is 0, and then A looks random, so it has a lot of three-term progressions, so we are done. Or A has structure in the sense that its Gauss norm is positive. And now, so we need to study the structured case. So in order to do this, we need now to define what is a nil system. So let L be a K-state nilpotent Lie group. So here's the definition of what it means to be nilpotent. And let gamma be a discrete co-compact subgroup. And also we suppose that we have a group homomorphism from some group G into L. And then we let G act on the nil manifold that we achieved when we divide L by gamma. This is some compact space. And this dynamical system is, so X is called the K-step nil manifold, and Gx is called the K-step nil system. Here is an example, which is called the Heisenberg nil system. L is just this upper matrices where you have 1, 1 on the diagonal, and here you have freedom to choose 3 parameters. Gamma is a lattice, 1, 1, 1, but here you, as you can see, you are free to put 3 integers. And if you divide L by gamma, you get a manifold. It's 3-dimensional, but if you divide R by Z, you get the circle, right? So the first guess would be that this gives maybe the three-dimensional torus, but it is not the three-dimensional torus. It's actually a circle fibration over the two-dimensional torus, but this fibration is non-trivial. It's not a three-dimensional torus. And you can, for example, define the dynamics by one generator. You just choose an element in L. So usually we choose 1, 1, 1 alpha and beta, such that alpha and beta are incommensurable. And then we can act with this element from the left on the cosets. And we get the Heisenberg-Nil system, and it's minimal, it's uniquely ergodic, and so on. In any case, returning to where we were, so we are faced with the following question. We have some function, it's bounded by 1. It has some positive Gauss norm, and we want to conclude something about the function. So we introduce now the notion of a basic Nil space, a Nil sequence of order K. It's a sequence of the form F, T, and X0. So here Xt is a K-step Nil system. X0 is some point in X. And what we are doing, we are following the orbit of X0 under this T. I remind you that T is a translation, so it's achieved by multiplying cosets by the left, from the left, by some fixed element G in L. And the sequence we just read, we have some function on our Nil manifold F, and we just read the values we get when we follow the sequence of X0. And now we have a very deep theorem by Green, Cow, and Ziegler, which tells us that for every delta and every d, there exists some n which depends, and this is very important, only on delta and d, and another constant c which depends only on delta and d, such that for any function from zp to r, where p is prime, such that the uniformity d dorm is bigger or equals than delta, and the function is bounded by 1, then there exists a basic Nil sequence of bounded complexity which correlates with this sequence, and the correlation is bigger than C. I didn't say what is bounded complexity, so I don't want to define it exactly, but it's clear that you want a function to have some bounded Lipschitz constant for this to be non-trivial. So that's one component of bounded complexity. You can also, if you want, order the Nil manifolds, because up to isomorphism, there is only a countable number of them. So that's another ingredient of bounded complexity. But the key point of this is that positive Gauss norm implies correlation with a Nil sequence. And this correlation, as you can see, is bounded below by a number which only depends on delta and d. Okay, now the next step is actually to use this information that we correlate with a Nil sequence in order, in the structured case, in order to find arithmetic progressions. This is also non-trivial. I will not discuss the detail. This goes back to a technique by Roth from the 50s. But intuitively, notice that a very particular example of a Nil sequence is when your Nil manifold is a circle and you just take the irrational rotation. So conceptually, Nil systems are generalizations of irrational rotations on the circle, which are of course very related to arithmetic progressions. So I don't think it's so surprising that correlation with Nil sequence can show that there exists non-trivial arithmetic progression. In any case, so the important fact is the Gauss norms inverse theorem. That's a very non-trivial fact. The proof by Green, Tau, and Ziegler has more than 100 pages, very complicated. And Szegedy, his idea was to find a more conceptual proof. So his idea was that if the theorem is false, then we can find a sequence of n1 over n counterexamples. That is a function fn which have this positive universally bounded from below Gauss norms that do not correlate with Nil sequence of Bowden complexity. And he wanted to use these counterexamples in order to achieve a contradiction, and he chose to use non-standard analysis. So he considered the ultra product of ZPN over some non-principal ultra filter, where he used the so-called Loeb measure. Then he defined the Gauss seminorms in this context. And here is the key point. He defined the characteristic Fourier sigma algebra of order K to be the largest sigma algebra Fk for which, so as you can see, a big difference between this context and the context where Gauss worked, where the group was a finite abelian group, is that the Gauss expressions are not norms, they are only semi-norms, and therefore we can define a Fourier sigma algebra of order K, or we can define a Fourier sigma algebra for a function for which this is a norm. Now, this is quite complicated. One complication is that Fk is not separable. But returning to our subject, this is exactly where the Nilspaces were born. Because he was able to show that when you project on this Fk, so this is the projection on Fk here below, it actually factors through an object, which is called a k-step Nilspace, which I will define shortly. One of the structural results that he was able to prove for these objects was that it's inverse limits of Nilspaces. And using the fact that such a projection factors through a Nilspace and the structural theorem, he was able to achieve a counterexample. Excuse me, he was able to achieve the contradiction. So he was able to prove the theorem. So this is the place where the Nilspaces appear for the first time. And you can see all the details, because I agree that there were many details here that I couldn't I couldn't discuss. We don't have time for that, unfortunately. But you can find it in the paper by Candela and Szegedy in Krell that appeared a year ago. In any case, now I think it's time to define what are Nilspaces. I think I have convinced you that they are important. As you can see, they appear in as the main structural component of a very deep theorem, the inverse theorem on Gauss norm, which is used in a very deep theorem by Green and Tau, as we saw, allowing us to solve some linear equations in the primes. So we will now introduce the Nilspace axioms, And we will do it in the dynamical world. So the Nilspaces, some of them are dynamical, some of them are not. We actually will consider only the dynamical ones. So we aim to develop a theory of parallelepipeds and Gauss norms in a dynamical settings. So here I remind the definition of the Gauss norm for a finite abelian group. Now let Gx be a topological dynamical system. So it's given by a big continuous action where X is compact metric space, G is a topological group. So Ex is X, GHX is GHX. And we will usually assume that Gx is minimal. That is that every orbit, Gx, G is in G closure is all of X. And we will now, following the Gauss approach, we will define basic dynamical cubes in the form, you just take these sums omega I, gi, which we have already seen in the group, and you act on some element X in the phase space X. And so you get what we call basic dynamical cubes or parallelepipeds. But in order for this to work out, we need to take the closure. And then we get spaces of D cubes for every D. As you can see, these are, you take discrete D-dimensional cubes, and on each vertex you put some element in your phase space. So this lives in X to the power D-dimensional discrete cube. And without giving the details, it's important to note that you can also define the dynamical cubes for general G, not abelian. In that case, you need a different definition, of course, but it's possible. And we call this object X, comma, CGD, where D goes from 0 to infinity. So when D is 0, we just, this is the 1 point space. For D bigger than 0, we have given the definition. And we call this a dynamical cube space. And now let's see what are the properties of these dynamical cube spaces. If Gx is minimal, then the 1 cubes, so these are pairs. By definition, this is X, comma, Gx. And Gx can be anything, so we get that the 1 cubes are all the pairs. Also, it has certain symmetries. For example, if you take a cube C omega, and then each omega, you replace the zeros by 1 and the ones by zeros, then this will also be a cube. You can prove that. Also, when G is a finite abelian group, you have unique completion for corners, in the sense that if you know that here you have X, here you have X plus B, here you have X plus A, then here there is only one possible choice, it's X plus A plus B. So these facts motivate the following general definition. So we start by defining something which is called the discrete cube morphisms. First, we define these 4 functions, rho 0, rho 1, rho 2, and rho 3. You see these are very simple functions. Then we define a discrete cube morphism from an m-dimensional, discrete m-dimensional cube to an n-dimensional cube by saying that when you apply f to x1 to xm on the i's coordinate, this must be some pkxj. So this gives you some family of discrete cube morphisms. It includes permutations of the coordinates. It includes reflection, rotation, and so on. Okay, and one more terminology, an element in X to the power 0, 1, n, which is not necessarily an n cube, we will call it a configuration. And so here we have the Nilspace axioms, which appear in a paper by Antonin Camarena and Segedi from 2012. So this is a pair consisting of X, a compact space, and this collection of cubes for every n. Oh, I see here I used the shortening notation. So when I write square bracket n, I mean the discrete, excuse me, the discrete n-dimensional cube. So 0, 1 to the power n. We call this an ergodic Nilspace, or just a Nilspace. Sometimes we don't use this terminology of ergodic, of degree at most k if it has the following axioms. These are the 3 axioms. First of all, if you have a cube and you compose it with a discrete cube morphism, then you are a cube. So this is called cube invariance. Ergodicity is the fact that the 1 cubes are everything. And the third and most important axiom, which is called completion, is that if you are given a configuration defined on a corner, so this is a specification of elements on all elements of the discrete cube except 1. So we call it a corner or n corner. And in addition, we have the property that when you restrict this configuration to the faces, to the hyperfaces, which do not contain the missing element, so this Fi given by all elements where xi is 0, so when you have, you assume that you have the property that when you do this restriction, you get a bona fide cube of dimension n-1, then this axiom tells you that you can complete this configuration to a cube. So there exists a cube C such that it equals this F corner when you restrict to the corner. And also we want to talk about uniqueness. So K plus 1 uniqueness is when if you have 2 cubes of dimension K plus 1 such that they agree on the corners, then they agree. And so a Nilspace is an object which has proper axioms 1, 2, and 3. So it has cube invariance, ergodicity, and completion. And we call it a K-step Nilspace if it has K plus 1 uniqueness. So let's try to understand what are one-step Nilspaces. So one-step Nilspaces, we fix some arbitrary element in X, in this one-step Nilspace, and we call it 0. And we take A and B. Now, I claim that this configuration is a corner. Why? Because by ergodicity, 0B and 0A are both cubes. So as you can see, when I restrict to the to the hyperfaces of this 2-dimensional cube, which do not contain the missing element, I do get cubes of dimension 1. So by the third axiom, I can complete. I can put here something which will make this a 2-dimensional cube. Moreover, because it's a one-step Nilspace, this completion is unique. And I define now addition between A and B to be this unique element. So this is a cute exercise where you check that this is actually making X1 to be a compact abelian group. So one-step Nilspaces are compact abelian groups. Okay. Another important example is that if you take what we already saw before, so the K-step Nil systems, then if we have a minimal K-step Nil system, then when we do this dynamical cube space construction, we get a K-step Nilspace. So here you see why we call Nilspaces Nilspaces, because Nil systems give rise to Nilspaces. But it's important to remember that not every Nilspace is a Nil system or a Nil manifold. Okay, so what were Okay, I see. Maybe I should go a little bit faster. So maybe I will, here I discuss the so-called weak structure theorem, but let me jump over that. Maybe I will just state the so-called inverse limit representation theorem for dynamical Nilspaces. So the first theorem was the theorem by Hoskra and Mass from 2010, which said that if Zx is a minimal distal topological dynamical system such that Xz is a Nilspace of degree at most k, then Xz is the inverse limit of k-step Nil's system given by Z equivalent maps. And then together with Manners and Variu, we were able to generalize this to much more bigger family of groups, all groups which has dense compactly generated subgroups. So in particular, all finitely generated groups. The key point here is that we do not assume that the group G is abelian. And the theorem says that if Gx is a minimal topological dynamical system such that Xz is a Nilspace of degree at most k, then X is actually homomorphic to an algebraic and equivalent inverse limit of minimal k-step Nil systems. And this actually, the proof is even different than the proof given by Hoskra and Mass for their case, for the case G equals Z. So the takeaway from this is that in this context, a dynamical Nil space of order at most k is an inverse limit of Nil systems. And as we saw, a related structural result was used in the non-dynamical setting, was used by Szegedy in his program to prove the inverse theorem for Gauss norms. Okay, so now let me move to another application, which is related to Semeredis theorem, which we have already mentioned. So this was a theorem from 75. In 78, Fürstenberg gave a very famous proof. So what did Fürstenberg do? So we consider xb mu t to be a measure preserving system. That is, xb mu is a standard probability space, and t from x to x is a b-measurable invertible measure preserving map. We take some f, which is an L infinity. It's non-negative. It has a positive integral. And then Fürstenberg studied the following lim-inf. So it's a normalized sum over an integral of fx, ftnx up to ftknx. And he showed that this lim-inf is positive. And then he used something which we call now Fürstenberg correspondence principle in order to conclude Semeredis theorem. So what is going on here? Conceptually, think about this as an expression counting arithmetic progressions. Of course, we are here in the context of a measure preserving system, but as there is some way to go from the context of sets with upper positive density in the integers to this context of measure preserving systems. And so he proved the Fürstenberg, he proved Semeredis theorem. Actually, this started a very important subject in ergodic theory, which still is very active. One question that was left open from this proof was, does the integrand that appear here converge in L2, right? Because he was studying the integral. And this, as we will see, this question has a positive answer. Let me mention that the question of almost sure convergence for a general K of the same expression is still open. it's a very important open problem in ergodic theory. Okay, so Hostenkra 2005, Ziegler independently 2007 proved indeed that this expression converges in L2. And if we want to summarize the proof by Hostenkra, the key step is that you study something which we call now the Gowers-Hostenkra seminorm. So it's not a coincidence that this name appears, and it's not a coincidence that the expression here should remind you of what we saw before. So notice this is already the third appearance of such an expression. We started by seeing the definition by Gowers in the context of finite groups. Then we saw a definition by Szegedy in the context of non-standard analysis. Of course, actually, Szegedy was inspired by the work of Hostenkra, where it was before that proven that this expression which appears here is a seminorm. So what do we see here? We see here a product over these cubes or parallelepipeds. Again, we have this epsilon n, here epsilon is the discrete cube. And as you can see, we are taking here a normalization. Again, this is not surprising. So again, it's non-trivial, this is non-negative, it's non-trivial, this is a seminorm, but it is. And the key idea is to study the sigma algebra where the seminorm becomes a norm. So we have already seen this idea. So this is exactly what says here, that this expression goes to 0 if the Gauss-Hostenkra seminorm is 0. So this expression, the Gauss-Hostenkra seminorm, controls the so-called non-conventional ergodic average. I should mention this is called the non-conventional ergodic average that because when k is 1, so when you have the 1 over n sum f tnx, this is the regular ergodic average, which was studied by von Neumann, Birkhoff, and so on. Here I wrote an example for k equals 2. So when k equals 2, you really see the two-dimensional parallelepiped, right? We have here fx, fn1x, f2nx, fn plus 1, n plus 2. Okay, and so to give some more details of how this is proven, this is proven by the so-called characteristic factors method. So this was defined by Furstenberg and Weiss in '96. We say that a factor is characteristic for the non-conventional ergodic average. Maybe I should say here something about notation. The NCK is the one where we write up to k plus 1. Okay? In this subject, as we have already seen, there is a shift by 1, and one should always remember this. It's quite confusing. So in any case, a factor is called characteristic if you have this non-conventional ergodic average, but actually this goes to 0 if and only if the projection on the factor goes to 0. So that's why this difference converges to 0 in L2 norm. And what Hostenkra proved was that given an ergodic measure preserving system, then it has a characteristic factor for the non-conventional ergodic average, which has a strictly ergodic topological model, which is an inverse limit of k-step Nil's systems. So this is quite remarkable. We start by a question in measured dynamics, right? We have some function in L infinity of some measure, and we asked if this converges in L2. And suddenly, it turns out that this is controlled by a factor, which is an inverse limit of smooth systems. So you may say, out of the blue, in measured dynamics, we got smooth structure. Now, I think that when you see this, you may say, but wait a second, the inverse limit of Nil systems, we have already seen this. And indeed, this motivates the approach to this theorem, to the Hostkra structure theorem, which I took together with Zhengxin Lian. So I should say that this paper is very complicated. The proof is very non-trivial. And we wanted to achieve a simplification. And the idea was the following. We showed by induction that there is a characteristic factor for the non-conventional ergodic average, which is a dynamical Nil space. And because the Nil space is a topological object which has these three simple axioms, this is much easier than showing directly that there is a characteristic factor which is an inverse limit of Nil systems. So in a way, we divided the task into two. First, we showed that there is a characteristic factor which is a dynamical Nil space. And then we use the theorem which I already mentioned by Freddie Manners, Peter Vario, and myself, which says that if G has a dense compactly generated subgroup, then Gx can be, and you do the cube space construction, then you get actually and you know that this cube space is a Nil space of degree at most case, then it's an inverse limit of minimal k-step Nil systems. And this, for example, gives us also a new proof for the Hostkra structure theorem for ZK, let's say. So when you have several commuting generators, which appeared first in the PhD of Grismer. So I have 5 minutes. So let me maybe discuss a third application very quickly of Nilspaces. And this is in the context of structure theorems in topological dynamics, which is also, so in topological dynamics, the subject of structure theorems has a long history. I will not go into the history, but maybe the best example is the structure of equicontinuous systems. So we say that the topological dynamical system is equicontinuous if for every G, so if for every epsilon there exists the delta such that, and this is the key point for every G, we have that dx, the distance between x and 1 and x2 is smaller than delta. This implies that G, the distance between gx1 and gx2 is smaller than epsilon for all G. And then you can wonder what are equicontinuous systems. Clearly, irrational rotation on the circle is equicontinuous. You can also give non-abelian examples here. I'm sorry, I'm missing. So SONR acts on Rn on Sn minus 1, which can be achieved as the quotient of SONR with SON minus 1. So here should be a quotient. In any case, you can show that the minimal equicontinuous dynamical system is a homogeneous space. So X is K over H, where K is a compact group, H is a closed subgroup. So this is a very good example of a structure theorem in topological dynamics. You start with some property, equicontinuity in this case, and you get a structure theorem, you show that the space is a homogeneous space. And then, for example, you can start asking if a general minimal topological dynamical system can be reduced to a minimal equicontinuous factor. And because I don't have much time, let me just say that this is done using the language of equivalence relations, which should also be equivariant. And so there is a whole history. We will not go over it, but in order to mention the Nilspaces, just let me mention that we can define the so-called maximal pro-Nil factor of a system. This is a factor of a general system, which is an inverse limit of Nil system and is maximal with respect to this property. And in joint work with Glasner and Ye, we introduced a family of relations which we called nilpotent regionally proximal relations. And here the key difficulty is to prove that these relations are equivalence relations in the generality of minimal actions. So this is this property here. And then we used the structure theorem mentioned before by Manners, Vario, and myself to show that these equivalence relations correspond to the maximal d-step pro-Nil factor. So these relations enable us to start with a general minimal system under some mild topological assumptions on G, and reduce it in the sense that we can divide out by this relation and get the maximal d-step pro-Nil factor. Okay, this was very quick. I think I will end here. So to summarize, we saw 3 different applications of Nilspaces in 3 different areas. I was not able to give many of the details, but I hope that I arouse your curiosity. Thank you very much.
Thank you. Okay, so it's time for questions, comments, and remarks. Okay, I see that there is one question. So please.
Okay, hello. You presented inverse limit representation theorem and Hostenkrag theorem. And my question is, could you show us some applications of these 2 theorems in number theory?
Yes, so this was actually, you can argue that Szeged's approach is exactly that. Because he was able to prove the inverse theorem on Gauer's norms using this inverse limit theorem. Just that he worked in the setting of non-conventional analysis. Basically, if you are able, I mean, the philosophy is the following. If you are able to reduce to an inverse limit of Nil system or Nil manifold, you may be able to prove what you want to prove because these objects are much more manageable.
So there isn't some strong connection to this theorems about sequences of primes like 4x plus 3y when x and y are primes, some this Green and Tau theorems, right?
There is or there isn't? I didn't get it.
Is a question, right? Is there?
Okay. And so I see that I went too fast, so maybe it was not good. There is a relation. That's the point. The point is that in order to solve these equations, you are, after a series of reductions which are non-trivial, you are reduced to this question of inverse limits.
Okay, thank you very much.
I agree with you that I was not able to give the details, but you can check the reference which I mentioned, and there you will see all the details.
Okay, do we have some more questions? Well, I'm hesitating a little bit since my question is not, in fact, crystallized, but nevertheless, let me ask it. So the crucial notion in this investigation is the notion of the density of the set. This is some sort of measure, but it is not a strictly measure in the sense of measure theory.
Right.
And this is very similar. So maybe let me also give some more background to my question. So I'm interested in particular in functional analysis, Hilbert spaces, and there is this well-known theorem that every infinite dimensional separable Hilbert spaces, in fact, there is one, yes? So even those spaces which look very large at the first sight, like a Fock spaces and so on, infinite tensor product, stabilized with some sequence, all of them are separable. But there is one instance when one encounters non-separable Hilbert space, and this is the space of almost periodic functions in the sense of Bezikovich. And if you take a look on the norm of on the maybe scalar product of the space, this is very much in the spirit of a density. So I'm wondering whether this space has any applications in those, I don't know, proofs in this theory.
I don't know about such a connection, but maybe there is. I don't know.
Okay. And one moment, okay, if you could wait for Mike. Okay.
If I remember well, there was a moment when it was a question raised about L2 convergence of some
Correct.
integrand.
Yes.
Yeah. So maybe this could be some relation with what Adam is speaking about.
I don't know, and I'm not quite convinced since, okay, how this space is defined. One can start with almost periodic continuous functions. So this is a linear span of functions of e to the power I s t indexed by t. So continuum many functions. And with respect to this inner products, all of them are orthogonal. And then you can just take a completion, some abstract completion. So from this description, you don't see how this space looks like, okay? It is just an abstract completion, but in fact, one can give another characterization. And of course, it is then L2 on some space, but the question is, what is the space? So the space is the so-called Bohr compactification of real numbers with Haar measure. So this real numbers are treated as uncountable discrete group, okay? And you take a Pontryagin dual, but with respect to discrete topology. So in some sense, you are taking, not in some sense, in precise sense, you are taking all possible characters, not only continuous one, all possible characters. There are plenty of them. And this space, as it follows from the general Pontryagin duality as a dual space for something which is discrete, it is compact. So it has a Haar measure, and this measure is finite, probabilistic, in fact. And one can identify this Bezikovich space of almost periodic function as a Hilbert space with L2 with respect to Haar measure on this Bohr compactification. So, and this Bohr compactification is a little bit like a stone-check compactification. It's not something which is concrete since those non-continuous homomorphisms are necessarily non-measurable. So it is like a solution of a Cauchy, functional Cauchy equation, which is non-continuous, so non-measurable in particular.
So here you have something similar, because if you think about the arithmetic progression, and you want to fill this arithmetic progression with some non-periodic distribution of primes, for instance. So this is something like quasi-periodic. It's like trying to speak about something which is not periodic, thinking about periodic things. So
Okay, probably you're
maybe there
right.
is a loose analogy, but
Uh-huh.
the mechanism is maybe
Yes.
there is some analog of the Bohr compactification behind this picture.
Mhm.
I don't know, but
It sounds
gut
like a
feeling is that
like a plausible
these things
direction
are
to.
similar. These
Mhm.
problems are
Mhm.
similar.
Okay, so it was more like a comment. Okay, do we have some more questions from the on-site audience? So let me also check whether there is something on a Zoom, but I don't see any raised hands. So if it is not the case, so let us thank our speaker again. So thank you.
Thank you.
And let me stop recording.